And we are starting. Is it working? It is. I think we are live, guys. Day 6. Streaming every single day. We're going to get this project to the end. We're going to have the 3.3 billion open source, truly open source checkpoints published in a couple of weeks, maybe months. Might be a bit more realistic, but with the support and attention I've been getting over the last days, I'm so hyped up. We have so many people who want to contribute to this project, to be champions for different languages. Okay, there is currently a person from the Eleutheri community who just said, "Hello, I'm Chris. I'm active in Eleutheri Polyglot project, which is an amazing project that's been doing similar things over the past." So we have so many people gathering. I'm so happy about this. Let's just see. Let me just give me a second. So we have this open NLLB list of language champions, and we basically have people applying to be the go-to person for a particular language. And the fun fact was, a couple of days ago, this was the best thing ever. We had someone who spoke Central Kurdish on the stream. We had like maybe 6-7 people, and among them was a person that, while I was playing with Kurdish, I was trying to debug something with Kurdish. A person said, "Hey, I speak Central Kurdish," and I was like, I realized how big of a deal this project can be. So I'm super excited, guys. I'm really excited. Let me just reply to Chris. Okay, guys. Let's get started. So let me open up my VS Code. Just a second. Okay, so this is the Stopes library. We need to open up. We need to open up the. Well, yeah. Actually, we need Stopes. Let's turn on my AC. It's getting warm in Belgrade. Okay, guys. By the way, do you hear me? Can somebody reply in the chat whether you can hear me or not? So where we stopped last night is we figured out that the script I'm using here for filtering, the get primary dataset script, had some issues because of the NLLB dataset, which has basically script as the part of the language code. And so because of that, it was complaining. So now I want to rerun this and basically fix. I want to fix this particular function so that we can include all of the primary data sets that we have. And then after that, we're going to focus on the second script, which is called compute length factors. Pozdrav Zvezdane. Yeah, I'll continue speaking in English. I'm not sure how many people are, whether we just have Serbians in the chat currently, but anyhow, welcome. If this is your first time, FYI, join the channel here, Meta NLLB Replication, if this project is of interest to you. We're looking for people who are going to help around their native languages. I assume your language is Serbian, so maybe you can help with Serbian. So if that's interesting, just join the channel here in my Discord. Okay, let's start. Let me kick off the run again. Let me run this and see the output. So we're gonna hit this skipping line here quite a lot, as you can see here, and all of the files we are skipping are in the NLLB dataset, pretty much. Let me see. Or some that have weird infixes, like this one. This is Tigray language. ET stands for Ethiopia, ER for Eritrea. So let me see. NLLB seed. So you see, this is causing the issues. The fact that we have script as a part of the directory as well as of the actual file with data. So let's see how we can fix this. What is the issue? Why is it complaining? Because it cannot find the source here, because let me see. Okay, let's just add a conditional breakpoint here. Let's just see if the corpus name equals NLLB seed. We want to hit the breakpoint, so let me rerun this. And let's see how this goes. So we have here data set. Why did this stop here? I'm not sure. Corpus name, this is not the right corpus name. Okay, let me see what happened here. Hey Venkatesh, this is not the video this is not the stream about that. We're gonna focus only on no language left behind, so machine translation for now. But maybe in the future, if I have some bandwidth, I might cover something like that. Let me just focus now here. NLLB seed. Just a second. This should be all right. This looks good. Why is it not hitting the right at the right moment? Oh, because I made a mistake. I have to put a breakpoint here, otherwise it overshoots by one loop. So we have to do corpus name here, and then NLLB seed, and this should now work. So if I stop and rerun, we're going to hit at the NLLB seed, exactly. So now what happens is we grab a bunch of different language directions. All of them have, as you can see, both the 3-letter code as well as the script as part of the direction. So let's go here, we grab direction, and when we split, we get source and target that includes the scripts. So that's the issue. So now I clean this here. You're a 3D artist. Yeah, anyhow, we are doing machine translation. We are basically enabling you to translate from 202 different languages using neural networks. That's a TLDR. Hey Ahmad, thanks a lot. Thanks for the kind words. Welcome to the stream. Check out again, guys, check out this channel in my server, Meta NLLB Replication, if you want to join the effort. If you speak some native language like Arabic or whatnot, we have a language champion list that you can join and contribute there. Just join the channel, you'll see more information. Let me just focus now on this. So let me see how this is gonna work. We're looking for, so this is the issue. We're trying to find, using glob, we're trying to find files, but this is gonna omit, we're gonna miss out on all of the relevant languages if we do this. Let me just think for a second. So source target. If we don't do this, we have to include script here, otherwise we will not find the files, because if you saw back there, here we have the NLLB seed. Let me find it. And then underneath it, no, actually, did I process? Let me see the processing I have for NLLB seed here. Do I have any renaming going on? So the new file name is actually, okay, it's actually gonna have the language code, the 3-letter language code. This was a mistake. I should have not changed the language code like this. This might be a bit of in the trenches work, not the most exciting work, but we have to do this. We split the source path to get the file name. So what's the issue here? We're going to find, we actually found the file, but then let's see what happens next. So here we construct the file here, English, Latin, MRI. Do we actually have that file? English, MRI. MRI, Latin MRI is the file we're looking for. And so this will not exist. And so it's gonna skip it. Okay. So just some errors on my side. Hey Vasim, we are not actually focusing on speech here. We're focusing only on text. The Seamless M4T paper, if you're referring to it, we just skimmed through it just to get some feeling for the Meta's latest work, but we are not working on that. As for what we've done, well, there was a ton of things. We got familiar with various code bases like FairStack, like GPT-NeoX, like Laser as well. I downloaded the data, I've done some processing. We're now at the filtering stage. We found the mine data from LNAI. There's been a ton of stuff that's been going on, but people can contribute by basically becoming the language champion for the languages they speak as the natives. And so if that's of interest to you, check out the Discord server on this channel, the Meta NLLB replication channel, and you'll be able to check the pin posts, and you'll see the Google Doc where you can put your name if you're curious to, if you're happy to contribute to the project, to your language, etc., etc. Okay, so how we construct this target file name is by grabbing the source file name and then just modifying the suffix. And that logic is not going to work for NLLB seed because, as you can see here, the prefix is actually different as well. Okay. So because of that, we have to change the logic for how we find the source files and the target files. We never have the GZ, so we can skip that one. Like, I'm almost certain, let me just see, assert that this thing is always, actually always 0. And let's rerun just to make sure that hypothesis makes sense. Let me disable this for a second and let me rerun. Okay, something's weird going on here. Yes, there will be many things you'll potentially be able to contribute. I'm gonna leave that I'm gonna chart out the plan for the next steps for the community after the stream. I just need to go on a break and think about it in a dedicated fashion. I can't do it on the fly like this. But 100% you will have opportunities to contribute. On the non-data side as well. Okay, why are you complaining? And before you were not complaining. Source file name. Oh, okay, because I have an error here. I made a typo here accidentally. Okay. Let's rerun. Okay, again, basically no GZ files. So we can remove this now. The hypothesis has been verified. Now let's go and focus on source global. So how do we do this? We want to grab, I'm going to make sure that the data structure is such that we always have two files. So because of that, we can change the logic here. We can do something like this. Target. Ignore the GZ. And then we trade like this. We remove this. We make sure we always have two files here. Actually, we don't need this assert. So we don't need to iterate here at all. We can remove this. Go back here. We don't need this. We don't need this. We just repeat the same logic for target. So we get target file name. We don't need this. We can ignore this as well. And finally, source path is going to be this. And this should be it. I think now this should work. I've modified this function quite radically. And I think it should work now. grabbing direction, finding the suffixes, which are the language codes, finding the actual files corresponding to those, making sure they're not zero, then grabbing the actual paths. Maybe we can put an assert here. This should be 1 and looking good, guys. Let's just double check this makes sense. Let's step through this file. Once this is done, we will continue on to the next config preparation file. So we need to set up these configs so we can run the filtering pipeline. That's kind of the TLDR here. Grab the corpus name, grab the directories underneath it, direction, source target. We find the files. We find the files here. Okay. We assert. We grab the file name. We grab the file name here. And we construct the actual file here. We don't even need to do this then. Why not just source path is actually this, right? Or not. Let me just double check something. So this is actually, no, this is actually a full path. So because of that, we can just do something like this. I'm just simplifying things a bit here. Okay. Okay, this is now looking better. Let's rerun. Here we are, here we are, here we are. And we just add that to the data set. And we keep on doing that. Let me just hit F5 and see when do we hit an issue. So we hit the issue with this one, okay, English, and then this is completely messing it up. We can't have Tigray with ET. This is out of distribution. We always have, when I say out of distribution, I mean it's not following the structure we have. Let's see. What do we want to do in this particular case? So we probably found, okay, we found a file there, but we didn't find we did not find a file here because we tried and looked for TIR, whereas in reality, we have what? Let me close up this one. What's the name of this corpus? Tico. So Tico has these guys. And you can see here that, yeah, I'm not sure what to do here. I think for now we can just skip this until we understand what exactly the difference is between Eritrea and Ethiopia. dialects or languages. If they are the same, we can just collapse them to the same thing. So maybe we can put, if the length is like this, then we skip. So this should now prevent us from failing there. Okay, so as you can see here, we are skipping a couple of data sets, this one, and also this one. Let me just add a to-do here. See how to handle here, ET, here, ER, and Latin. This is from Tico. Okay, looking good. Obviously, this will require a lot of back and forth. We are still just dealing with primary data. We'll later have to include mine data as well. But I'm just trying to push through the pipeline once so we can kick off a training run. Okay. So we end up with a YAML file. Train primary. This is the one. We end up with this long file. This is the output of this program. Basically a set of data sets for different language directions, which data sets are there for that language direction, and then we have the paths to the parallel corpus to bytext. Okay. Now let's go and run the second script. So let's go from prepare data, populate data config. Let's go to compute length factors. That's the second function we have to run, so that we end up with a config here. The length factors config. This basically tells us how much more verbose a particular language is compared to English. So English is obviously 1 because it's the reference point, and then we'll look at how more verbose different languages are. So let's see what's the kind of the max here and what's the min. It looks like some languages, like this looks like potentially Chinese. I might be wrong. Let's see what this language is. It's Chinese, but some particular script probably. Simplified Chinese is Zohans. Let's see whether we have anything with 4, 5, 3. We have these two with 3. So this one is these ones are the most verbose. And what's the smallest one? You have 0.6 somewhere. 5, 4, no, 7. Okay, so there's a couple of languages which are much more succinct than English. That's fun. Let's rerun. How do we, okay, compute length factors. Let's go here. Did I modify this? I think I did. Required false. Flores. Filter configs. We don't have to rerun this because I already ran it. Let me just double check that we need to. Thanks a lot, Navjot. Thanks for the kind words. Let me just see for a second. Let's go to Stopes. length vectors. Okay, this can be done by running, you'll need to create configuration files containing the list of corpora and the set of length vectors. Okay, this command will run using the output directory and the data config directory as specified above, and will additionally load the default example config. Why did they set floors there? Aha, because it says floor as path. Okay, fair enough. So that's our calibration dataset. That's what we use to estimate the verbosity of the language, floors. Let's quickly skim through the main function, just to understand what it does. So it opens the length vectors YAML. Just a second, let me open up the script. Okay. And then we save dump, we get the scaling vectors given the floors path. So it grabs the dev sets and then goes through it, splits, gets the language, we read it, and we dump it into the vectors. Fair enough. And then we compare that against English. Let me quickly skim through the Flores dataset. So we have FairSec Flores 200 dataset. Here it is. So they just focus on what? Only on dev, not on dev test. And they go through all of these languages here. They remove this removes the dev and the dot suffix, and then they replace this with this. Fair enough. And we finally end up with length vectors. Okay. Fair enough. 200 languages here. What I think we should do is, instead of using 3-letter codes, because there's some ambiguity, sometimes there are, as you can see here, 2 languages that differ only by the script, Arab or Latin. We need to, I'm going to leave a to-do for later. For now, we can just continue like this. But I think what we need to do is go here and add a big to-do. Instead of 3-letter codes, let's use the format Okay, I think that's what we need to do. Okay. And we're done for now. Now let's go to the filtering file and see how we can run this. So again, there's going to be the example config, which we're going to analyze in a second. Here it is. Let me just split it to right here. And we're going to now see whether this config makes sense. That's the first thing. And also, let's just consult the README here. So this is how we run it. Filter, we specify the output directory and the data config directory. Anything not specified will be set to default values specified in data types filter config. That's what I want to see as well. Let's see that filter config. Let's open up that guy somewhere here. Filter config. Is there any mention here of filter config? There is. Apologies. Let me just open this. Let me open it up here. And let's analyze the script line by line. Okay. So, included corpora. We'll have to obviously expand this list to support all of the datasets we care about. Toxicity filter, LID filter, all of that is set to none. Did I modify this file before? I did. I added a couple of examples here. Okay. This was just the initial run I ran before I even started streaming. I was just playing a bit with the NLLB repo. So let's see how do we go about this. Do I have, let me just see what I have long JSON specified for filtering. Yes, we do. Here it is. So this is how you specify Hydra config. Output directory will be in filter out. Here. And filter configs is the data config file. Okay, so this is what we want to use for filtering. This is the filtering config. Now let's go back to filtering. Let me close this down. So we make the output directory. We do some logging. We open the config YAML and we just write the config we are using for filtering there. That's again just logistics, so that we can later figure out how did we get the output files using which config. That's for reproducibility purposes. Then we go through these guys, and from config we get that particular group. So that means for train primary we get all of this. For train mind and for back translated data, we don't have anything specified at the moment. And then we call filter group. Okay. So what filter group does is it creates an executor This can be either local executor or this can be Slurm. I took some time to basically set up my Ubuntu machine as a Slurm cluster, so that's we can run it as a Slurm as well, even though I have only 2 GPUs on my local server. Slurm cluster. I'm gonna refer to my 2 GPU rig as a Slurm cluster. It feels better. And then partition, number of nodes, number of CPUs per task. Memory 128. I don't have that much. I have 64. So I can maybe specify 32 there, so that I don't eat my whole memory, or maybe 48. Then we grab the configuration from here. We assert that either included corpora is none or excluded corpora is none. Something has to be none. Okay, so we don't have excluded corpora. This is where we specify the previously created configs. Those are these guys, the length vectors in the train primary. And then we open up we load the length vectors. And then in the context of this, we use the context manager of this executor to do the following thing. This is just some logging. So what do? We go through the data sets, which is specified. Okay, those are the ones we just computed. Those are our data sets. And then we go through direction corpora. If direction is not specified in the configs directions, so that means here, then we continue. Okay, so that means, let me leave a to do here. I'm not sure what's we do specify all directions from train primary YAML. Then we grab the source and target from the direction. And then if the included corpora is not none, then we do what? We iterate through the corpora items just a second. Let's open up this guy to just see what's the structure there again. direction corpora datasets. Okay, corpora will be this. So corpora items is going to give us corpus name and dataset. This is the dataset. And so if that corpus name is included in the included corpora, okay, so we have to go and grab all of these and add them to example. So let me add an additional to do. Okay. And then we grab the data sets for that particular direction. Fair enough. If there are no data sets, we skip. Otherwise, we assert that there is total. Wait, the assert total is not in. Is a reserved name, okay? And then we specify group name. Direction, that's going to be the output. And then we submit a job. And the job consists of what? We call the filter direction function. We specify the group name, which is going to be train primary for us because we are currently focusing only on the primary dataset. We specify the directions and the datasets that we are processing, the length vectors, the group name. Isn't this the same as this one? Wait. Yes, it is. Group config. Oh no, we grab the whole config, sorry. And then output, and then just custom step name is going to be group name followed by direction. Let's see what this filtering does. Hey, Pulkit, no worries. So basically, we're trying to open source the no language left behind checkpoints, which is a model that allows you to translate between 202 human languages. That's the TLDR. How did you find out about the channel? Curious. Maybe write it down in the chat. Or also, if you didn't see this, join the Discord server, join this particular channel, Meta NLLB replication, and then you'll find much more context there as well. Okay, so filter direction. Let's see what's going on here. We create direction, and then we instantiate a ton of different filters. And those filters are basically specified here, right? So as you can see here, under train primary, we have all of these additional keys in the YAML. All of those files are gonna all of those settings are gonna specify some filters. So we have laser filter. Awesome, thanks, Pulkit. So we have laser filter, which is not specified, which means we will not instantiate that one. We have length filter, which is specified, and here are the configurations for that particular filter. And then we have LID filter, which is currently null. We have toxicity filter, which is null. We have dedup filter, which is pairs to true. And then, yeah, okay, we can maybe, we'll definitely have to consult the paper to see what's the best way to filter this. Again, it's going to be highly iterative. We might have to do stuff our way. We might have to run multiple instances, multiple training runs to see what works, what doesn't work. but we're gonna try and stay as grounded as possible to the actual paper. So after the filters have been created there, then we do what? Then we create this, we create some outputs, source, target as zip archives, and then YAML okay. If the file already exists, then we skip this iteration. Otherwise, we enter this logic here. And what do we do there? We open the path out source. So we open up the source. That's going to be the filtered source data. And this one is set to none for some reason. Okay. So the target language is not none, and it's usually not. Okay, then it will be a mono. Okay, this helps with filtering the monolingual as well, which we will not be doing. Otherwise, we just do parallel. So I think we can just add a cert here. We can add a cert, or no, I don't want to. No, let's just keep it like this. Maybe people will want to use it in different ways. So we open up the source, the directory file, so that we can put some filtered data there. And then we go for a line in inputs. What's inputs? Inputs is going to be, okay, dataset reader, and we pass in the dataset and the corpus name. Okay, and then we go line by line through our parallel corpus. And then if we specified normalize Unicode, we call and normalize the Unicode, obviously. Let me see whether that's specified. It's not. Normalize punctuation, that is specified. And then we go through the filters and use all of those filters to potentially filter the line. So if it's none, we break. And then we continue. Otherwise, we write that line to the source or target. And that's it. Then if we have dataset counts, we note it down here into counts, which is just a dictionary of string keys and filtering counts object. And we dump this object as well. Okay, I understood what's going on. So we're basically applying the most important lines are here. This one, let me put the breakpoint there. And then we need to see whether we want to do this for our data. Do we want to normalize Unicode? Do we want to normalize punctuation? Do we want to do this? That's a reasonable question. Okay, let's put some breakpoints there. With the current config, we will be entering here, but not here. Okay. So as far as I can tell, by analyzing the filter script, what we need to do is these two to-dos. And just, let's analyze the configs now a bit. Cluster is set to local. We can always set that to we can set that to slurm, but we don't want to for now. Once we have more compute on some of the clusters, that we will apply, we will apply for our grant, by the way. So then we can start using slurm. But until then, we can ignore that. There are the directions, all that is good. Now let's see what happens here. We specify some defaults for dedup, for toxicity, for LID, which stands for language identification detection, length filter, and base config. So we opened up this. Let's see. Train primary. Optional. Everything else is specified. So we did specify this in the launch JSON. This is already specified in our example. This is also specified in our example. This is set to none. Let's check what is this. Okay. So you can see here. Included corpora, we did specify that here. Normalized punctuation, this is set to true, this is set to false. Again, this is the same here. Normalized punctuation is set to true. The other one will be false. And then there is the laser filter, length filter, LID, toxicity. They just use default values. Let me put this on the side here. So what's going on? We have for this one we override its settings. So it looks toxicity set to null explicitly, LID set to none explicitly, length set here, and laser not even set. Okay, so let's go one by one. Let me now open up dedup, this guy. Here it is. The target is going to be, so this is the actual function that's going to be doing the filtering. We have dedup pair set to true, max target set to null, max source, we don't even have it. So that means it's going to be set to none as well. So we only dedup pairs. Let's quickly consult the paper here. I remember they mentioned something like this in the paper. When do we want to do deduplication? Luckily, not that many matches for this word. Okay, I'm fairly sure this is data cleaning for what? For monolingual data scale. The margin-based criterion of our mining approach requires unique sentences, but the sentence splitting and cleaning process might generate a lot of duplicate content, so we run a global deduplication process. Okay. Let's go through this one. So demonstrates that training data deduplication is critical for large language model training. It's important for machine translation as well. So in the final step of the filtering pipeline, we remove duplicates. In order to determine if two texts are duplicates, we apply a normalization process, which removes punctuation and non-printing characters, then replaces all digits. The filtering can remove pair duplicates, defined as cases where two data points have identical source and target. Fair enough. Or source/target duplicates, i.e. data points that have the same source side but might have different targets, and vice versa. Source deduplication is useful for back translated data to catch cases where the back translation model decodes to the same sequence regardless of its input. Okay. Same source. Target deduplication is useful for mind, where same source sentences are aligned with multiple target sentences. Okay, so that means for now we just care about pair deduplication, right? The effect of filtering is discussed there. Filtering leads to an improvement in performance as well as a reduction in hallucinated toxicity. Our filtering configuration for various data sources is made available along with our other training scripts. Fair enough. I didn't see anything. Okay, let's now focus on the deduplication filter. Okay, so you can see here, we just have set this dedup pairs. And everything else is set to none. So this is supposed to do, I guess, source and target deduplication. I'm not sure why they have max as a prefix here. And then the target. Let's quickly analyze this class. And then we'll work our way from here all the way up to these other 4 filters. And then we can kick off our preliminary filtering run, filter the data, and then we can proceed to the next stage. And in the next stage, we'll be using SPM200 tokenizer to basically binarize and shard our data, and then we can kick off a training run, maybe, just maybe even tonight. That would be amazing. Okay, let's go. Class dedup filter. Filtering filters, dedup filter. Okay, let's go here. Pair deduplication. Source and target. And then filter line, which is the line we are calling, if you remember, in our main filtering logic. So here we're gonna just set a breakpoint here, but let's quickly skim what's going on. So we'll be doing this because we have this is set to true for us, and we have the target line. So we're gonna call normalize for dedup, and we pass a line. And so let's see what this does. So it strips all of the, I guess, white spaces from left and right. This is what the split function does. And then if the line does not exist, if not line, return line. Okay, we return none. We lowercase it. So we do the digit. So we basically grab a digit and we replace it with 0 always. So that's what we saw in the paper as well. So we find the digit and then we replace it, and then we also take punctuation or non-printing characters and we subtract. We find them and then we just remove them, right? compile this plus this and replace this with this. Fair enough. Let's see what this does. Compiles Unicode punctuation. Here is the Unicode punctuation. So this is actually a dictionary, right? So what they do is they grab keys, apparently. They grab keys here. Okay, these are some weird Unicode characters. And they grab the keys and they join them with empty, with nothing. And then that means we have a group of those weird characters. That's it. That's the punctuation logic. And then additionally, we add to that list this list. Okay, so now I understand why they do this, because you'll end up with two groups, and so we'll have these brackets because of this merging here, and we just replace that. Okay, makes sense. Now it makes sense. Let's just quickly see what this does. So non-printing characters are what? We compile, and then we go from 0 to 32. I guess this is ASCII logic, right? In ASCII. And then also, so that's one list, and then the second list is here. We just add them. We map those into characters, and then we join that, and we create a group. Okay, this makes sense. Let's quickly open up, just for fun's sake. Whoops, not that. That's not the point. Let's just open the browser tab here, and let's open ASCII table. If we open up the ASCII table, so we said what? We said 0 through 32 not included, and 127 through 160 not included. 160 is not included. So 0 through 31. So here, so these are the guys, right? And then here we start having the printable characters. So these are just control sequences and whatnot. So null, start of heading, blah, 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 blah. None of them are printable. And then also 127 through 159. 127 is the delete key through 159. These weird guys. Am I even? These are printable characters. Why are we? Maybe I'm misunderstanding something. If somebody knows this, let me know in the chat. Okay. So now we do that. We replace that, and then we replace additionally tabs. Okay, so that's basically what explained in the paper, right? Let me just reopen the paper. We'll be referring to paper quite a lot, so let's just quickly. Apply normalization, which removes punctuation and non-printing, then replaces all digits. That's it. That's the explanation of this code we just saw. Now let's go back to dedup. So here, that's what we do here. That's what we do with the source and the target sentence. And if we're doing this, then we convert this to string. If it's not none, then we append the normalized one. Fair enough. And only then do we apply hash. And if it's not, if we haven't seen this so far, so this is how we are doing the duplication. If we have seen it, then we return none, because we want to filter out duplicates, right? That's why we're doing this. Otherwise, we just add the line here. Makes sense. If target, we don't care about it, we don't care about that. So that's the whole logic, guys. Basically, we normalize the sentences, we hash them using this function, and then we check for duplicates. That's it. fairly simple. I understand this completely now. Let's quickly see what do they do for target and source deduplication. For target and source, they grab the normalized target line, they hash it, and then if this value is bigger than target dedupe, wait. Oh, okay, got it. That's why we have max. This now makes sense, guys. So only if the line appeared more than a certain amount of times, then we filter it out. Otherwise, we just add +1. Okay, makes sense, makes sense. So there is some level of generalization there. We allow to have non-perfect deduplication. Makes sense. Okay, dedupe done. Let's go to the second one. Let's go to the toxicity filter config. I'm not sure what I've done there. Let's quickly skim through the toxicity filter. So here it is. Here's the toxicity filter. I'm not sure what TWL stands for. This is English porn TWL path. Data toxicity TXT. Do we have this already? Large experiment seamless NLLB data toxicity. Max toxicity difference. Max toxicity. And some two weird files that we don't maybe even have. So let's see whether we have them. Let's go Ctrl-Shift-P. And then there are no matching results. Okay, let's try and search for this online. Let's see whether they did store this file somewhere. Meta, no language left behind. Where can we find these files? Let's maybe go to the issues section. Let's go to the issues section in NLLB. Let's open up the issues here and let's see whether somebody mentions this complete file. Hey, I'm new here. Can you please explain me very short what this series is about? Hey, Ganesh, we're basically trying to open source a checkpoint for no language left behind project, which allows you to translate between 202 human languages. So we're just trying to get the checkpoints trained. 3.3 billion is going to be some first target. We're going to open source that so everybody can use it for commercial purposes, and then we'll probably even go beyond that. But that's a TLDR. TLD, not R, but like W, I guess. Didn't watch. Okay, let's see if we type in this, we don't get anything. So let's just type in porn. A weird, okay, weird thing to write here. Research President Biden. Yeah, TLD, I've never pronounced it out loud. TLDW, okay. Let's go to Stopes. I don't see anybody mentioning this here. Maybe I should stop saying that word. Maybe YouTube will ban me. What does TWL stand for? Thermal work limit, certainly. The weakest link. By the way, Ganesh, check out the Discord server Meta NLLB or application channel. Basically, That's where we're gonna find all the necessary context. Okay. What's this? Let's maybe try and just type in TWL here. Nothing in FairSec. Completely nothing. Stopes. Let's open up Stopes. Let's open up issues. Let's type in the word. Let's type in toxic. I don't see anything mentioned. Nothing there. Let's try the word. Okay, this is hopeless. Maybe. Let me think for a second. Let's try toxic here. Okay, we're gonna open up an issue if we don't find anything. Let's see in the paper. So what do they say about toxicity filter? Based on techniques proposed in section 7.3, we implement a toxicity filter. This removes sentence pairs which have toxicity imbalance, i.e. when the difference in number of toxic items detected in source and target is above a certain threshold. An alternative mode of operation supported by the filter is to remove all pairs in which one or both contain toxic elements above a given threshold, regardless of their relative difference. Further details in section 7.3.3. 7.3.3. Okay. Okay, guys, let's see how this goes. Oops. Toxicity. We created a dataset of toxic words for all 200 languages by combining automatic and human evaluations. Okay. Section 7 traces the automatic and human evaluations of our translation, including the detection of catastrophic and toxic translations. Toxicity 200 word list to detect toxicity in 200 languages. Okay, so let me just open up. Let me open up my Notion here on the side, so I can type in things here. So we are looking for, I'm gonna submit an issue if we don't find these. Submit an issue to FairSec regarding the NLLB project. Basically, toxicity 200 word list. What's up with that one? Where is it? And then let me just put this on the side so I can see you guys if you're asking any questions or anything. Okay, and then what else? What else? Okay, so you can see they have Flores 200, which they use as the eval, and they have toxicity 200, and then they have the human evaluation as well. Fair enough. And then we open source these novel toxicity lists for all 200 languages. They say that on page 72, but I didn't see it anywhere. Okay, let's go further. This is like the detective work almost. Is it this one? Hey, if you find something, let me know. It will be super awesome. I don't see any link. If you're sending any links, YouTube Live might block you, so I might not see your message for some reason. Let me quickly skim through this, see what's going on here. Toxicity detection in digital content has received significant attention. We provide the first baseline to evaluate toxicity in a massive number of languages by collecting and releasing the word lists. And then they mentioned toxicity detectors that can be optimized in precision or recall depending on the particular application. Then we propose a filtering strategy to mitigate toxicity imbalance. And visualize the source contributions. Okay. What is toxicity? It can be present in the source, or it can be generated de novo. Okay. Note that added toxicity represents one of several types of catastrophic mistranslations. You obviously don't want to hallucinate a toxic language. Obviously it varies. Collection methodology. By the way, why are we, this is page 80, why is this here? Okay, this is just some bug. Okay, this is how they collect it, not necessarily relevant to us right now. The average list length is 271 entries, and the median number of entries is 143. The latter might be a better measure of central tendency than the mean average, given that languages with a rich inflectional morphology constitute extreme outliers. Czech list has 2,000. Czechs and Polish folks have 2,500 toxic words. The longest one has 6,000. Okay, this is probably more because of the nature of the language, as they say, inflectional morphology. So you can create slight combinations, slight variations, but still have the same meaning. Okay, what we are interested in is where is the list, where are the detectors? Do we want to reuse that? Do we want to train our own potentially? We're not aware of machine translation analysis. The values added toxicity. Okay, so they're literally using just a heuristic-based approach. Can you link that, Pulkit? Number of toxic items and match toxicity, illustrated in figures 27. Can you send it to Discord? Can you please send it here? What's your Discord? Is it also Pulkit? No, I don't see you. Maybe you can join the Discord there and just send it to Discord. So again, they're not using a machine learning approach here. They're just using word lists for 200 languages. Okay. And then they say this is illustrated in figure 27. Two criteria: number of toxic items and matched toxicity. We define toxic items as short n-grams, 1 through 4, most commonly. One or more toxic item and 2 or more. Matched or non-matched? Present in both sides. Awesome, thanks a lot. This is amazing, man. Thanks a ton. Thanks a ton. This is, you contributed on the live stream. This is amazing. Let's save it. Let's save it to, let's go to home, let's go to my projects, let's go to NLLB, let's go to, where do we want to save it? Let's go to FairSec. So we have floors there already, so let's just save this there. No, this is really super helpful. We're gonna read this immediately after we are done with the paper. Amazing. Again, thanks a ton, man. Okay, let's go and wrap up the paper reading. Let me see where it is. Where is my paper? Here. Let's just wrap up the reading so we have a bit more context on how to use this exactly. Therefore, we have the following toxicity detectors options. 1+ toxic item non-matched, 2+ non-matched, 1+ matched, 2+ items matched. So 4 classes. We track the number of unique toxic onions found in the line, but do not count a phrase again if it has multiple occurrences. Okay. For some languages, space localization is not sufficient to distinguish words from one another. We utilize sentence piece localization of both the sentences and the toxic word list. Okay, you cannot work, you have to work in the tokenizer space as opposed to into textual domain. Fair enough. Let's just quickly skim through these guys. Let's just skim the conclusion part. Okay. Okay. Fair enough. Let me just quickly skim through the mentions of toxicity down below. Some languages have a ton out of English. Some languages have a ton of toxic terms apparently. Percentage of Flores 200 dev test lines with candidate toxic terms detected in translations with NLLB 200 both into and out of English. Okay. So how should we interpret this? This is log scale, by the way, on the x-axis, 0, 1, 1, 10, which means we have huge outliers. This language, TWI, let me just double check. What's TWI? Let's see the code here. TWI, covered by macro language AK. What's this? Twi. Where is it spoken? In Ghana. Okay. It seems Ghana people curse a lot. That I might be misinterpreting this information here, but for some reason there is a ton of curses there. Let's see what else. Again, today we're working on filtering, so I think it's very important for us to internalize all of this information. When translating out of English compared to translating into English. Out of English, we have more than 3 times as many potential added toxicity examples. Whether these differences are due to an overdetection by our lists or due to an actual added toxicity by our models when translating particular is a direction for future work. So maybe, yeah. Let's quickly skim through this. Our goal is to produce high quality, safe translations. Not desired, but adding toxicity is worse. The +1 toxic item detector to evaluate the added toxicity. We conduct our evaluation on the floor step test. It's Wikimedia domain, so it's just lower toxicity domain in general. Potential added toxicity with the +1 in 130 out of 201 from English and 200 into English. Okay. Sorry guys, just skim this. We've been through this. Related work. We've been through this as well. We were here. Let's quickly skim this. Okay, to quantify the quality of our lists and detectors, we aim to utilize a general purpose toxicity benchmark first, before application to machine translation. We used a jigsaw dataset, which aims to take an input sentence and detect if this sentence is toxic or not. Okay. We used the test set partition available from the first challenge and filtered comments by applying these criteria. Lines with less than 600 characters, less than 100 words, and with at least 1 word token. Okay, and then they translated using NLLB model the results in table 26. Okay. Don't want to spend too much time. This is something that somebody could do, like a single person could literally internalize this and help us focus on this later. For now, I just want to be pragmatic and understand how to use this and get some context, but not too much. 2 plus matched. Okay. Let's just see this. We used our detectors, 1 plus toxic item non-matched, to count potentially toxic items in the bytext training data. Figure 29 shows percentage of toxic items per corpora in the English side of our bytext pairs only. That's the figure 29. Okay, let's check it out soon. And then figure 30 shows the percentages of toxic items per corpora in the non-English side. Okay. Varies among languages and corpora. Open subtitles and QED have a larger amount of potential toxicity in several languages, and mine data has a lower amount. We examined a sample of the potential toxicity of these corpora and found that a greater proportion were misaligned text by text. Fair enough. Toxicity was present only in one side of these bytext, either through complete omission, by far the most common, or significant detoxification. Training in this kind of misaligned bytext can encourage mistranslations with added toxicity. Okay, this is going to be fun. This is the part that we care about. How do they filter it? Let's just quickly skim through this. So for English, for 60%, so we have the highest F1 score for English, obviously, of 1 plus toxic found. So open subtitles, you can see it's the most read one. Bible is neutral. Okay. And here, NLLB seed seems to have quite a lot of toxicity. Interesting. Okay, let's go through the filtering, because that's the leitmotif of this stream. So we're gonna focus on filtering again for those of you who just joined. Added toxicity can arise from toxic items present in the training data set. The objective of the filtering is to detect imbalances which could eventually generate toxic mistranslations. Note that we do not want to filter out all toxicity, because this would introduce bias and prevent the model from correctly translating potentially toxic items even under benign usage. Wait, this... Okay. We propose to filter training sentences that contain a difference of multiple toxic items when comparing the source and target sites. Fair enough. So they are looking for imbalance. That's the key takeaway there. To test this methodology, we included toxicity filtering into the filtering pipeline, which will be described in more detail in section 8.1.4. We then trained bilingual models with and without this filtering. And the table 27 shows results on the dev split of floors to 100. We observed that a filtering pipeline which includes toxicity filtering not only improves the performance, but also tends to reduce the number of toxic items in translations. Okay. Interesting. I wonder how much data they filter out. Okay, they say here. After filtering, there is a ton of data removed. 7.3 million to 3.8. 10.2 to 6.2. This is a significant reduction of the data, yet they get better results apparently. Wait, toxicity doesn't change. Almost 2211, 2244. It's even worse here. It's a bit better here. It's a bit better here. But we obviously get higher quality translations. That's interesting. Okay, so here are just some examples. Ethical considerations, unintended use. While acknowledging potential unintended uses of our list, we remain mindful of the likely possibility that similar lists may have already been separately collected for the aforementioned purposes by entities who have not publicly disclosed them. Fair enough. Okay, so they mentioned section 831 for filtering. Let me just see. Let's go up there. 814. Okay, let's go to 814. They briefly mentioned toxicity here. Okay, that's all they mentioned here. So now let's go and see the README that Toolkit sent. So here is the actual list. And it's amazing you found this again. The lists were collected via human translation. The files are in zip format. And unzipping is password protected. Interesting. Okay, BCP 47. That was the thing I was mentioning. We want to go BCP 47 actually. We want to go and have the ISO 6393 base tag and then supplemental tag to identify the script. That was the word I was looking for. That's what we want to do later. So let me just let me quickly open this. Okay. That's the name of the code. The code mirror those used for the release of the Flores 200. However, in cases where Flores 200 targets a specific lect, may not be as restrictive. Okay, let me just double check. What's this? Can we find that on Wikipedia? We can. Okay, there is a ton of scripts. Let's find Cyrillic. Each script is given both a 4-letter code and a numeric code. Okay. Here are the list of codes. So good thing is all of them are 4-letter codes. Fairly predictable. Okay. Let's just find Cyrillic for a second. This is how the script is written. Version, number of characters. Okay. Awesome, awesome, awesome. I'm gonna put this on the side here so that we have both the ISO codes as well as the okay, awesome. Let's go back here. These are the supported languages. Estonian, French, and Dutch have been updated. Okay. Let's try and now unzip this. and then start analyzing the code base. The toxicity filters, I mean. Let's see, let's go here. So we are back here. Let's find no, this is Stopes. Let's open up the FairSec. Here it is. Let's find, let me just close this down. Let us find the new zip. Here it is. Let's see whether we can just extract here. Extract. Okay, we can. And then inside there, there is a ton of... Guys, how does one compute how many of these we have? Okay, 204. I see now. So let's try and open one of them. Like maybe, let me pick a language I speak. Serbian is my mother language, my native language. This one, let's try and extract here. It's password protected. Okay. Okay, I now understand what TWL stands for. Toxicity word list. Makes sense. Okay, guys, I'm gonna move this off the camera just so that we don't get sued by YouTube. And let me read some of these. Okay, I already see some errors because basically I see both Latin script as well as Cyrillic. And I understand now why they are mentioning that the morphology, the inflections make a difference, because they're basically quote unquote conjugating. That's not the right, that's used only for verbs, but like variations of the same nouns. Yeah, this is definitely not the best script. Not the best list. I could easily improve this for Serbian language. So we can add that to do somewhere. Let me quickly add a to do. So that we can community effort, maybe people can improve these lists. Okay, that's one thing we could improve. Let me just open one more. Let me just open something that's fun on the screen so you can look at something. Like maybe this, so people know what we are looking at, what we're working on. Okay, let me go and unzip the English Latin. Let me find the English. English Latin. Let's unzip this. Again, we have to pass the password. And let me open up the English list. This is a much more comprehensive list than the one in Serbian. Just the pure length of it. It's like 1,117 words, whereas the Serbian one had. That's one of the reasons I really want to work on this project. Like, I think we need to make sure that non-English languages are also we have high quality LLMs, we have good translations. That's just something that I'm very passionate about. Okay, let's go back to the let's go back to the code. Let's open the stopes. Here we are. So let me just see whether that's the right format of these lists. We have BCP code, TWL, TXT. That's right. That's right. So we have these files, but I still don't see this one. Let's see how it's used. Let's go to the toxicity filter. Let's go to the toxicity filter under, what's the right path here? Is it this one? Filtering, pipelines, filtering, filters. Exactly. So this is the actual filter. Let's analyze it the same way we analyzed deduplication. Okay. Let's see. So we have, what are the settings we can pass? We can pass in max toxicity. We just open it up here. So we have max toxicity, which I didn't know what it is for. So we have that one. We have max toxicity difference. Okay, so that's the difference between number of detections in the source versus target direction. Then we have the target toxicity list, and we have the source list. Let's see how those are going to be populated. So we form the, that's how we grab the toxicity list for a particular language. And then if this is not none, then we append it. Why would we add English PORN? I don't want to read it out loud on the stream. To a non-English language. What would that do? Does that make sense? And so if it exists, then we create a toxicity list. And toxicity list is probably just a data class. No, it's not. It's actually a bit more complex. It's just a class object. Okay. Let's see what that one does. Okay. So we create a toxicity list. We grab the path, and then we do what? We go through those paths. We open them up as textual files. We go through the lines. We strip the lines. We tokenize the lines. And then we add those tokenized versions to toxicity, as well as lower. Why would we create lower cap for tokenized text? Okay, let's quickly see what this does. A very simple way of tokenizing the toxicity detection. So we grab the line, we strip it from left and right, remove the white spaces, then we replace the Unicode punctuation, which basically does what? We grab the Unicode punctuation, we go through the characters in the text, and we try and get the corresponding punctuation. If we don't find it, then we just return the character. Okay, makes sense, makes sense. So we just replace these weird ones with the normal ones. This weird comma, weird dot. Why do these even exist, if anybody knows? Like, why do we have 2 question marks? Why would one have 2 codes for the same symbol? I guess that's beyond me. Let's maybe ask. Maybe we can ask in the channel. Somebody might know something like this. Okay. And this is where this can be found. Let me just grab the path of this file. Okay. Let's continue here. So let's go back to toxicity. So we replace the Unicode punctuation. Okay, makes sense. And then we do what? We split on punctuation, symbols, and hand characters. Interesting. So we split. Whatever we find, we replace with what? Wait, what does this exactly do? Regex compile on punctuation, on symbols, and on hand characters. But what does this do exactly? Let's use ChatGPT to figure out this line. So we're getting closer and closer to implementing the filtering pipeline. I feel excited. What does the following Python line do? Okay, and this part is interesting. This is the replacement pattern for the matched portion of the string. First captured group. Okay, and what's the first group? The first group is symbols. So here is the definition of split. What's the first captured group? Can you further clarify your previous reply? According to the ChatGPT, exactly. Any punctuation refers to hand. It's literally perfectly correct. Standard ASCII question mark, commonly used in most Western scripts. Full width question mark is used in East Asian languages such as Chinese. But why? It looks literally the same. What's the? Try and Google that. Zvezdan, try and Google it and see whether you find a bit more insights. That's useful. It's already giving me some hints, but like, yeah. Got it. So that's the whole thing is a group. So let's consider an input string S. The comma would match the pattern. The exclamation mark would also match the pattern. The Chinese would match the pattern as well. Then the regular, when the expression is performed, each matched character will be replaced with a space, followed by the matched and then space. So using the input example, we would end up with something like this. Okay, got it. To tokenize text by separating punctuation marks, symbols, and Chinese with spaces, which might be useful in certain types of natural language processing or text analysis tasks. Makes sense, makes sense. Yeah, I mean, to my eyes, and I think to any human's eyes, those two could be like it's like the difference in a font of a textual character. Like you can render obviously not like letter A in multiple ways, but it's still the same thing, and you always represent it with using the same code. So why do we have multiple code points for those two representations? That's weird. I'm confused there. Okay, so okay, I understand this part. Split on punctuation symbols collapse multiple spaces. So we split here and we collapse multiple spaces, fair enough, and add spaces before and after. This allows us to use fast substring matching without running the risk of getting false positives due to subtoken matches. Okay, so that's what tokenization does, and then we just add those and we lowercase. So now I understand why lowercase. When they said tokenize, they literally thought they are using tokenizer, but in the sense of transformer tokenizer. Okay, and then there is the toxicity count, which does what? We grab the input line, we replace the punctuation, we tokenize it, and then we ask for t in the toxicity. If it's present, then we sum and we get the regular one, and then we get the lowercase, and we find the max. So that's how we find the number of. Got it, makes complete sense. Now this is kind of obviously very much a big heuristic, and I have no idea how this can fail across multiple different scripts that span 202 languages, but it roughly makes sense what they do. Okay, I understand it. Makes sense. Okay, let's go down there. So the part that's confusing is why would you add English porn? Okay, and then load target lists. Makes sense. And then filtering the lines works like this. So we still need to understand what happens with this. Why don't we have, where is this particular file stored? Where is this? And why is it not mentioned in the paper anywhere? It's not mentioned in the paper. Okay, I think, well, the reason is probably that all of us in our native languages, we use a lot of anglicisms, meaning a lot of English words, verbatim. And then I guess the hypothesis there is, let's add those to also filter toxicity no matter the language, just because of the pure prevalence of English text on the internet. I would love to create quickly issue on I guess what makes more sense. This is Stopes. So yeah, let's go to Stopes. Let's go to Stopes and let's open up an issue. Let's open up an issue here because I did not see this mentioned there anywhere. So that's hard coded where? That's hard coded in the Stopes. Toxicity filter config. Nor it is mentioned in the NLLB paper. Am I missing something out here? Okay. Let's just see the preview. Let's maybe just link to make their lives a bit easier. Let's go to Stopes. And then what's the Stopes pipelines? Stopes pipelines, and then what? Filtering configs.py. Toxicity. Here it is. Okay, let's just do something like this. And I think we can submit this. Okay. let's go back here. Just a second, let me just note this. Submitted an issue asking about a toxicity list. Okay. So let me just move this so you can see it. Let's go back to work. Submitted an issue. Okay. Waiting for a reply. This looks terrible currently. My notes look terrible. I'm gonna clean that up. But let's go and analyze everything else we need. You posted what you found in the Discord. What did you find? Right to left languages have question marks looking at the right direction. Okay, fair enough. But this one is not it. This one is literally just question mark and then followed. It's the same side. Same orientation. A square character cell is what I'm getting. In East Asian typography, they use square character cells. East Asians, such as Chinese, have their own typographic conventions and punctuation styles. The full width question mark is used to match the width of the characters around it and maintain visual harmony in the text. Okay. Compatibility with legacy character encodings. Okay, so like a TLDR is it's messy. Thanks a ton. Thanks, Wesdon. This was super useful. So let's go back to the filter line function. Let's see what exactly the list will do. So if it's not none, then we do what? Then we grab the line, we grab its source, we compute, we get the compute here. And if we are greater than that one, we add to the counts, we add +1, and we don't return the line. We filter out the line. And here for the target line, if line exists and if the toxicity list exists, then we do what? Then we again compute, and if it's greater, we return none. If it's not filtered out, then we ask what? We see if the source is not none. Okay, this is the difference. The difference computation. Let me think for a second. We go and do what? Toxicity count. We filter it out. Okay, if it's not filtered out by that, then finally we compute the source toxicity versus the target toxicity. And we see if the difference is bigger, then we return none. Okay, makes sense. But one thing, how can we ignore, how can we make sure that only this is filtering out stuff? I guess we can just put this to be a large enough number. That's one reply. Okay, if it's not none, okay, we can set it to none. If you set it to none, then we ignore all this filtering and we just focus on the difference in toxicities. Okay, makes sense. Guys, we are now familiar with how toxicity filter works. Let's continue. What's next? We've seen dedupe, we've seen toxicity. Let's go and analyze the LID filter. So now we can go and analyze the language ID. Okay. So there are some thresholds. Let me see, what do we use here? Lid filter is set in the example YAML, it's set to null by default. We override it with null. So let's see whether we actually want to use this or not. Okay. So thresholds. I'm not sure what it is. We're gonna find out soon enough. Default threshold, excluded languages, excluded corpora. Model path. We have to find this model. Let's see whether we can find it in our repo anywhere. I doubt it. I mean, you really have to just, obviously you have to download those. If anybody can find this one, that would be super useful. So that's Stopes. Let's go to Fairsec. Did I ever download this one? Fairsec, let's try here. No matching result. Okay, so final thing we can do as always is go to Stopes, go to issues, and let's see whether anyone mentions this file. Nope. Let's see whether somebody mentions that file here in Fairsec. No one. Okay, so we don't know where to find LID for now. But anyway, let me just store this README somewhere. Okay, we already did. That's fine. Let's go back to LID. So, LID filtering. There is the LID filter and there is the model. Let's first analyze the code. We can probably infer what's going on even without reading the paper. I think this probably won't be useful because in the construction of the data sets is where this LID was used. I'm not sure whether we're going to use it to actually filter additionally our training data set. So let's see what's going on. So let's search for it. Let's find the filter under LID filter. Here it is. Is this the one? Let's just double check. That's the path. Filtering filters LID, filtering filters LID. That's it. Let's see what it does. So it gets the thresholds, tries and gets a threshold for the source and for the target language from here, from this dictionary. Exclude the corpora, languages, fast text, load model. Okay. This we should probably find. We'll probably find this model under fast text repo. I guess that's the answer. So quickly we can immediately double check that. If we grab this file, if we go to fast text, if we go to the actual repo and let's search for this in the issues maybe, or just see where we can download stuff, there's no mention of this, but let's see where we can download something. Download the model, compile, download the model. Looks like a decent candidate. Does anybody mention this? Let's see whether we can just Google for this. Nope. Fast text. Nope. Language as the argument, overwrite, and then command download calls the download model from util. Okay, let's see where that one is. Where can we find the util file? Where can we find the util file? Let's go to where is the, just a second. Maybe under source. Oh, this is some. Nope. Where is this? How do we import? Okay. Okay, if somebody can double check for me here. We are looking for what? We are looking for okay, I'm slowly starting to engage people there. Just spreading some tasks. It's going to be easier like that. Okay, so let's go again. Let's go to the LID. So assuming we load the actual model somehow, let's see what the filter line function does. So the function does the following. If the excluded corpora exists and the line is, and line's corpus is particularly in that excluded corpora, okay, so that means we don't do filtering for a particular set of corpora. Makes sense. Store LID probs in the dataset line. Let's see what that does. So we have predict, because this is obviously a neural network. We pass in the line k set to -1. Have no idea what that means. K set to -1. What would be k in the context of this model? K fast text. K is what? Controls for the number of returned labels. A choice of 5 will return the 5 most probable labels. By default, this returns only the most likely label and probability. Okay. Fair enough. So -1 basically gives us the highest probability item language. So the language and the probability, okay? And then what do? We go through those and we create the probabilities, or -1 returns us everything. Whatever. We'll see. We'll kind of infer what's going on from the code. So then we go and grab, we're interested in our source language. What's the probability? Okay. And then we say what? If target language exists, we do prediction for target as well. And same logic again. We try and get the target LID probability. And then once we have the probabilities, if the threshold is set and this language is not excluded, then if we're below threshold, we filter it out. Okay, fair enough. Fairly simple. And then the second line here, if target language is specified and target threshold exists, and then if this is not excluded, then again we filter it out. Okay, fair enough. So now that we understand the LID filter, a couple of questions remain. Oh, nice. Thanks. Meta already provided toxicity lists, but if you think this could help us additionally, love to hear the rationale. Okay, let's see. LID filter, where are we? We want to go to the paper and see how do they use LID, if that makes sense. So let's go to the paper and let's see LID. The thing I hate about Chrome is it possible that in 2023 I still can specify at least like full word here as a parameter, like so it's catching these, it's matching solidified here with LID. If anybody knows, like I did install previously some extension, but I didn't really use it that much. If you know any extension that can help me search through documents, that would be super helpful. Otherwise, we are hitting a ton of false positives. We first develop, okay. Let's see how the filtering works. Scaling LID, models, training data and handling imbalance, improving LID, that's not what we care about. We care about only filtering. Okay, here is the mention filtering the training data. Is this training data for monolingual or what? Models. Let's see what this section is about. Language identification. Automatically creating translation training data. So that means primary, that means mind and back translated. Let's see what's up here. Script detection. Table 3. LID, performance of LID on floor is 200. That's true. You're right, but like in some cases you can't do that. And also sometimes when the LID starts, you might lose some, right? It's not perfect heuristic, because sometimes it's the first word and then there is no space, and sometimes it's the last word, so there is no space. There is a dot or whatnot. We select 74 low resource languages on which are we built okay, confusion, okay, applying language ID, but this is for the monolingual pipeline. Low LID scores in our monolingual, again, this is monolingual data. Luckily, LID is fairly uncommon infix. Okay, this is again conclusion. Okay. Okay, LID filtering. I think this is the one, right? This is the filtering strategy that we've been looking at for large. This is for large scale back translation though. Mind, and then let's see what they say here. Discard pairs whose sentences do not appear to be written in the expected languages. This can be performed automatically using LID with thresholds chosen appropriately based on the reliability of LID scores for each given language. Section 5.1. Where can we find those scores? It's gonna be fun. We filter the fine-tuning data using LID. And length-based filtering. I guess we can experiment with this if they didn't mention anywhere. Validation, LID, this guy. We can ping this one or Celebi guy. Maybe he knows a bit more. Janice. Okay, here are the LID results. Precision for different languages on Flores. Looks fairly high for most languages. I see a couple of outliers. I see KAM language, whatever that is. And then I saw Chinese somewhere. I see also TSN. I see YUE, Han. This is probably some Chinese. Let's see. YUE is what? We can immediately find out. YUE. Well, it doesn't seem to be mentioned there. Okay, so these are 200 languages. Okay, and then it drastically falls down, right? Here it's fairly high scores, and then here it's not as good. How many languages do we have here? Let me just quickly count. 1, 3, 5, 10, 15, 20, 25, 32. That means times 2, 64, and then 64 here. So that's 128, and they mentioned 200. So they did not report for all languages, or I'm missing something. Okay. Okay, so how do they actually filter? LID filter, did they mention something like that? LID filtering. With thresholds chosen appropriately based on the reliability. What does appropriate mean? Oh my god. Let me think. If anybody has any idea, let me know. LID scores. Low threshold. Section 5.1. Let's see whether they mention any scores here. The rise of large scale, blah, blah, blah. Okay, I don't see. I don't see anything mentioned here. Let's see, guys, let's see whether we have any mention of threshold. Let's skim through the threshold mentions just to see whether maybe this is what. Okay, here it is. Okay. I don't see the actual scores. Okay, then they say here, to this end we select 74 low resource languages on which our preliminary LID model yields low F1 scores. After a first run of language identification on web data, we randomly selected several thousand sentences across various languages for which prediction scores fell between 50 and 90%, chosen upon manual inspection, noticing that many classification errors were found within that range. Okay. Table 50. No actual mention of the scores. We are now at page 32. Let's quickly jump to table 50. Is that the one we saw before? It is. Okay. Given the domain mismatch, see the section 5.1. Our development set could not be utilized to tune the detection thresholds to a desired performance level. Instead, we relied on the distribution of model scores on the monolingual data of the paracrawl across all predicted languages. We chose that dataset based on the assumption that its distribution would realistically match that of common crawl. Okay. And that analysis motivated our choice of 0.5 as the default threshold in the first two cases, except for high resource where we could afford a more stringent value of 0.9 and still collect enough monolingual data in our downstream pipeline. In the last case, we picked values corresponding to the peak of each distribution, ranging from 0.2 to 0.4. Okay, so that's some insight about LID. So let me just mention this somewhere. Page, what was it, 35? Okay. First two cases are what? Extreme skew here, extreme skew here. What are the first two cases? Left skewed, rarely go below 0.5. Extremely skewed, almost all are above 0.9, and right skewed. Okay, so they use, for these two cases, they use 0.5 unless we're dealing with high resource. In the last case, so that's this case, we picked values corresponding to the peak of each distribution, which are ranging from 0.2 to 0.4. So now, where do we find these numbers? That's the question, right? So the peak of this distribution is like maybe, I don't know, 0.1. And this is for this Yoruba, or what's the name of this language? What's the Yor? I remember that was the Yoruba. Exactly. I'm slowly learning all of the languages, guys. It's the ultimate alpha. Threshold. Let me note this down. February 18th. For the third case, where the LID distribution for the language is heavily left skewed. Super useful to help out with LID detection. Any proposals to how to keep track of our tasks? Maybe we can have, the simplest thing would be just have a Google Doc or whatnot, or just use, or Notion. Notion might be a good thing. I think Notion is a very good place to keep track of stuff, or just some of those tools that are actually dedicated for task stuff, like Asana or whatnot. I have no idea, I haven't used it, but okay. Let's see whether there are any additional insights. Okay. But I again think this is more for, this was done in the monolingual dataset creation phase, which precedes the mining phase. Okay, this is just a threshold for mining. And this is what? This is for toxicity stuff. Toxicity. Laser filtering. That's a different thing. That's again for mining. Length filtering, LID. Chosen appropriately based. This is just for the 4-phase curriculum they're doing, where we include low resource languages later during the training process. That's the TLDR there. And we are done. That's it for the, okay, so not sure what we're gonna do about this. Even if we have access to the model, which I guess we can find it, we have to figure out the scores. That's A, and then B, do we really need this? I'm not sure what the, whether we need to do this. This is one of those things we'll have to experiment with. But for now, we understand what's going on, right? We can wrap our minds around it. So let's now jump to the next topic. The next topic is, we've done the deduplication, toxicity, LID. Let's see the length filtering. This one should be fairly easy, I guess. So length filter. By the way, let me see, did do? Okay. So let's go to the length filtering. Length filtering has a couple of options. Min length, max length. Here we've set it to 5 and 1050 in our example config. YAML. Max length ratio set to 9. Min source unique ratio set to none. And then there is the actual length filter class under filters. So let's just go there and find it. So again, length filter is here under filtering filters. Let's see how this goes. What's going on in here? So we set the min and the max and the ratio and this, which was none. And then we grab the length factors, which is, again, guys, remember, that's the thing we already computed, right? That's something we've done already. Here are the length factors. So again, that's how verbose the language is compared to English Latin script. Let's go back here. Let me just find, again, we lost it. Okay, here it is. Just pin that to the tab above there. So we grab that factor. We grab the factor for the target, and then finally the magic happens again in filter line. So if the source line does not exist, or if the target line tar is not none. Wait. What is this? Like empty or none? I guess that's what it's capturing. Not line. Why didn't they just do not line target? Line target is not none and not. Okay. Can't you just capture both cases by just a simple condition? Let's quickly check that. Why not? Let's just create a simple script here. Quickly, just a temporary file. And let's assume we have random dummy string, and let's make it this, and then let's make dummy string 2, which is going to be none. If not, let's run this. We printed both lines. So again, not will capture both none and empty, right? So that means if we go back to length, is not none and not, yeah, this is just redundant. Looks to be redundant. But the idea is, if any line is empty, then we just return none, i.e. we filter out that pair. Okay. Otherwise, why? This is confusing. But let's read through the rest of the function, then we'll figure it out. So if it's not none, so it exists, and if it's not empty, we filter it out. Why would you? That would filter out every sentence we have, which is weird. Okay, so if min length, max length, if any one of these is specified, then we go and calculate what? We calculate the source sentence length. We multiply it by the factor. Okay. Shouldn't we divide it by the factor? Could this be a bug? Because imagine the language is more verbose. In that case, the length factor would be higher than 1, and we would be additionally multiplying by a bigger number and already a larger sentence in expectation, so that would kind of double down instead of dividing. Or maybe I'm misinterpreting how the length factors are computed. Let me quickly double check. Compute length factors. What do? We we get the factor by doing what? So the factor is basically the length of that file, okay? And then, okay, got it, makes sense. So if the language is more verbose, then the coefficient will actually be smaller than 1. And then we multiply by that one here. Okay, that makes sense. So that's just a normalization so that we adjust to English so we can use a common threshold. So if the min length is specified and the source length is smaller than that, then we filter it out. Makes sense. If the max length is specified and if the source length is bigger than that, we filter it out. That makes sense. And then if the target line exists, then we compute the target length and we again repeat everything the same as above. Min, max filtering, and then max length ratio. If that exists, we compute the ratio like this if source is longer. Otherwise, we take this different coefficient. And if that ratio is bigger than the max ratio, we filter it out. And the ratio is set to the best of my recall, that was 9 always, max length ratio. Yeah, that's set to 9. I remember that from the paper as well. So again, all of that makes sense. And finally, this one, which I don't know what it is. Source minimum unique tokens. Rationale: in neural back translation, the decoder will occasionally get stuck in a loop and repeatedly produce the same sequence. This filter catches that. Okay, so this is more for back translated data, which we are not yet using, so we don't have to care about this for our primary data set. Min source unique ratio. The order is 6 for English, appropriately scaled for other languages. Okay, and then we compute what? N-grams for the source sentence. We pass in the order. Will min return, is min only returning integers? Again, let's just quickly test something here. So if we have something like this, let's put 1.32 here just to get, okay, so a minimum between these two. Why would we ever, then you're gonna always end up with 1, right? There is no way. So we always end up with 1 here, right? There is no way that this is gonna be so low so as to get lower than this. But quickly, let's just double check if that happens somehow. The minimum returns the actual floating point. Okay, so it's not going to. So this is weird then, because source factors, if you take a look at the length file, here's the length factors file, it's never gonna go that low. It's always around 1. Some of them are maybe 0.7. So in order to trigger this to go below 1, we'd have to be 1/6 or bigger, right? Or smaller, which is super low, which is like 0.18 or something, 1/6. So this is always 1 pretty much. And then if the length of the n-grams, then we filter it out. What does this do? If the length of that set is smaller than the length, okay, got it. If the unique tokens compared to the actual number of tokens, if that's too low, that means we had those repetitions and we filter it out. Okay, that's the logic. if you're following along. So let's go to n-grams quickly. N-grams strips the string, replaces the space with the empty string, and then goes over the length minus order plus 1 and grabs the n-grams, whereas the order is always going to be set to basically 1, right? So that means we're going to grab all of the characters. Because if we go back here, unless I'm really misunderstanding something here, this is always going to be 1. This is a bug, guys. This is obviously a bug. For English, this coefficient is 1. And that means if we print the order, instead of 6, which they said in the, we get 1. So that's a bug there. Okay, I'll push out these changes, by the way. I already created a repo for the NLLB branch. I didn't push out the soaps yet, but maybe a bit later. Okay, so everything makes sense. There is a small bug here, but there is this one. This might be bug as well, because let's put a breakpoint here, by the way, for later. So this catches the cases where we only have source or we only have target. But this one is super weird. So if it's not none and if it's not empty, then we filter it out. This looks like we'll be filtering everything out. Might be a bug as well. We'll see once we start running the pipeline, which is going to be very soon. And finally, we are at our final filter, which is going to be the laser filter, which we didn't even include here. So that means we'll be using default, which is none. Okay, so here's the laser config. So the only thing that's specified is this coefficient 1.06. And if we go to the laser filter, let's see what happens. Here is the laser filter. Fairly simple. We specify the threshold, and then if the line doesn't have a score, then we return the line, okay? Otherwise, if it has the score and if it's lower than the threshold, then we filter it out. Pre-computed laser scores to filter by text. Okay, this is something that's confusing. So let's try and understand what is going on there in the paper. Let's consult the paper. Let's see the laser filter. If that's mentioned anywhere, it is. Operates on mined data and can remove byte text pairs whose laser scores fall below a given threshold. We apply a threshold of 1.06 as we saw before. So that's more for the mined data, right? And hopefully that's been done by somebody else. Okay, we actually have a conversation going on here. Let me just quickly go through this. GitHub issues as well, sounds good. Sounds good. Or simply use Notion. And then let's see what else we have. Are you looking for the NLLB model? It's likely the 218 bin. Also, I recommend not to use the 218 due to licensing. There is a GPL alternative that does not deny any commercial use. Nice. The 157 version is CC BY, so it's okay, but 218 is CC BY NC, so the NC part stands for non-commercial. The one in fast-text docs is CC BY SA, share alike. Okay. Yeah, good point. Not sure about that. Okay, we're getting a lot of traction in the channel. That's amazing. Let's see. Laser filter. What exactly does this do? So laser, how it works is we embed a sentence from a source language, and then we embed the sentence from a target language. We get some embedding vectors, and then we basically do cosine similarity or some margin-based metric. They use the ratio for those margin metrics, and then they filter out so that they can find the parallel corpus. So I'm fairly sure we won't be using laser for primary, definitely not. So this is more for mine data, which I think is already processed. Yeah, we'll have to figure out those details along the way. Okay, guys. So that's it. We now understand the whole filtering procedure. There is also this normalized Unicode. I'm not sure what this is. Let's quickly understand that one as well. Normalized Unicode is called here. And if that's specified, then we basically do what? We get Unicode data normalize NFKC. We normalize the string, then we split it, and then we join it. What is this? What does this do? This is, I assume, also some package standard lib Unicode data. Okay, let's see what this does. Again, whom better to ask than the almighty ChatGPT? What does the following Python line do? Unicode normalization on the input using the NFKC normalization form, KC normalization form. Transforms different representations of the same character or sequence into a single canonical form. This helps in comparing, processing, and handling text that might have variations due to different Unicode encodings or decomposed forms. Python module, function, specifies normalization form. full width characters to their equivalent half width. If we don't get a satisfactory solution here, we can just go and analyze it on Google directly. So let's see how that works. Let's consider a few examples of how the given Python line might behave with different input strings. So given string, if we normalize, we get this that looks the same. I didn't notice any difference. It's probably hallucinating there. Okay, this makes sense. Okay. Let's see how this is used. Let's quickly see this. Here are a few code examples. Normalize. So we have the decompose. So it basically creates these two. Compose. Would convert this to this, okay? Both decompose forms convert a single combined character into two characters. Do the reverse, okay? And we are using what? We are using NFKC, so we are using the compose form. The two K forms are used to convert characters added to Unicode for compatibility purposes. When we apply the canonical decomposition, it doesn't do anything. However, the compatibility decomposition will return the corresponding compatible character. 1. Nice. Nice. Okay, let's just quickly see what this does. Okay, I think that's enough for now. So that's it. And now do we want to do this? Do we want to normalize Unicode or not? Should one do this for the primary dataset or not? That's the question. Let's go here. Paper. Normalize. There is only 5 mentions of normalize. Normalize Unicode. Let's see. Normalize encoding to UTF-8. I think we immediately found the solution. Wait, is it? This data has been pre-processed to remove all markup and approximately normalize encoding to UTF-8. Again, normalize Unicode. Okay. This is not relevant. We normalize our Arabic text by replacing different forms in the Arabic numerals. What's this? This is multi-dialectal translation, okay. Okay, that's it. Let's see mention of Unicode. To address this problem, we search for distribution shifts in characters, either by computing character histograms or by looking. Okay, this is for the, again, filtering the training data. Or LID. Scaling LID to more languages. Oh, all of this is under LID. Okay. Let's just read the length filtering one because we went through that one, but we didn't see this section in the paper. So the length-based filters identify sentences that are not within provided maximum and minima. It also filters out sentence pairs with highly skewed length ratios. The concept of length is not straightforward when working with a massively multilingual model due to the inherent differences in sentence length distributions across different languages. In order to account for this phenomenon, we measure sentence lengths based on Unicode code points and apply a language-specific correction factor. So we compute the factors. Okay. Concretely multiplying all lengths by this factor allows us to express a single length threshold in terms of typical English language character lengths and have a length discount or penalty applied with generally shorter or longer sentences, respectively. For mined and back translated data, we filter out sentences with length ratios above 9. For back translations, we additionally filter out sentences of length below 15, corresponding to about 3 words. Okay. So it's not completely clear when do we want to do this normalization of the Unicode. But it's set by default to false. Normalized punctuation, on the other hand, let's see what it does. We replace Unicode punctuation in the sentence by just grabbing, okay, this, we know what this does. Dealing with a bunch of scripts, bunch of languages is messy, as you can tell. Okay. Guys, let's now set up some reasonable filtering pipeline. Let's run it so that it can be running while I'm on the break between this stream and the next one, which starts around 3:30 p.m. CET, because I'm in Europe. So let's focus on that. Let's basically set this up. Let's see where we can start here. All of this looks good. We can ignore these two. So we have to set up the train primary. we have to set the, let's grab directions. So let's go to this file and let's grab all of our directions. Okay, to do that, let me create some script. Let's go here. Extract directions. We can use this one to read, I guess. Omega config data path. Let's just grab this path. Let's go here. So something like this, and then we can open it up. So let's open the YAML path. We'll have to import pathlib. I'm getting used to using pathlib. Usually I just use OS package. So pathlib. So how does one specify this here? Do I do just pathlib like this? Or no? Let me just quickly ask Copilot. How do I do this? Let's see whether this will work. We want to do reading. And then can we just do this? So we have omega to YAML, but is there from YAML or we can just use the built-in YAML, I assume. Is this built in? Let me open up my content environment. We just pip list this and see whether we have, do we have YAML there? Is that a standard library? Grab YAML. Nope. Okay. That's what I was looking for. Let's just see whether this will crash, because this doesn't make any sense. It's not pathlib, probably something like path. Okay, this might make sense. Just going on a feeling here of how a design should look like. Okay, it looks like I made it. So this is, yeah, this is working. So now we open this and then we'll load it, and then let's just print the YAML file and let's print whatever type. Okay, whatever. So let's just go here. Let's rerun this. Let's stop this and let's rerun it. Okay, did not crash. That's good. So we have a ton of different language directions. And now we basically want to grab the keys. What's the type of this? So the type is dictionary. So if we just grab temp keys, we get all of the language directions, and we have how many of them? Length of the keys is 574 directions. Okay, fair enough. So let's just copy this. Let's copy keys. I'm going to convert that into a string, and we can directly copy this from the terminal. So here are all of our directions. we grab them. Next time we can just have we can print the keys, and that's it. We can save that somewhere, but let's see how we can now populate our example and not create a mess out of it. So let's go here. So we are looking for what? We are looking for the example config. Here it is. So we need to plug in those directions in here. An alternative would be, let's modify this, otherwise this will become unyieldy in a second. Let's modify it by a path of the file that actually contains the directions, instead of enumerating all of them here directly and making this file completely unreadable. So let's see how this is consumed. We have directions. Let's go to the filter pipe. Let's search for directions. Okay. So what I would love to do here is okay. So let's just do one thing. Config. This is for filtering. Let's just modify the config somewhere in here, such that how do I know Sasha Seva and Misha Mladenovic? I used to train parkour, I used to train Kung Fu, and so Misha Mladenovic was a good friend from a buddy of mine. So that's how I know him. Sasha Seva, I don't really know that guy. Like, I know he's friends with some of my friends, so that's the reason. Completely unrelated. Okay, let's see. Let's grab config directions, and then from the path we're gonna now load the list from there. Okay, let's first see one thing. What do we get? What's the result now? If I run this, what do I get? Okay, I get a failure because I try to do what? I try to run with no args. I have to change the config. Now this should work. So directions will be what? It's just a list. Okay, so it's basically just a list. So let's reconstruct that. Type. This is actually just omega config list config. Got it. Oh, nice. Small world, man. Small world. Small Serbia, I guess. Directions. Let's open this up. and then we grab directions. No, we don't want to do that. We just want to read let's see what happens if we do this. And then we just do something like this. Okay, let me stop here. Let me stop and let me see what did I do here. So the changes, so we grab, instead of directions directly, we grab the path, we load the data there, and then we plug that into directions. That should work. Let's see. So now let's grab all of this. Let's go and create. Let's go and create what? Let's go and create this maybe here. Let me just save this here. How can we store this as a list? What's the best way to do this? What's a simple way to do this without having to curate and create a YAML config? My voice is dying. Okay. How can we do this? Well, I can always store this as a YAML config. Okay, I can store it as a YAML. That's actually a fairly simple thing to do. So we grab directions and then Copilot does its magic. Will this work? This should work. So let's dump it straight ahead there. Okay, let's run this code again. We load the config. We grab directions. We open directions and we dump this. And here it is. And that's all we needed. So now we can copy the path. We can go to filter method. And then we can specify directions in example here. And so we just do the following thing. We just say okay, this should be it. Let's call this directions path. Let's go to filter. And now let's rerun the code. Okay. Okay. There are some expectations on how this is supposed to look like, so let's not change that. Fair enough. Let's just leave it as it is. Go back to filter and let's rerun it. Okay, again, it's complaining because I changed this. Let's just do it like this then. Okay. Okay, guys, my battery is going to die right now. My battery just died.